So good afternoon, everyone, and welcome to today's seminar titled Performance Tuning of MPI Collectives, Status Quo and Open Problems. Our speaker today is Sascha Hunold, who is an associate professor at the Vienna University of Technology in Austria. His research focuses on MPI, OpenMP, scheduling algorithms, and reproducibility in the context of parallel computing. Sascha Hunold received his PhD degree in computer science from the University of Bayreuth, Germany, and his master's degree in computer science from the University of Halle-Wittenberg, Germany. Afterwards, he held postdoctoral positions in Berkeley, Grenoble, and Heidelberg. Sascha, thank you very much for accepting to be our speaker for today. We look forward to your talk.
Thank you very much for the introduction. I hope everyone can hear me well. Can you raise up the hand, the virtual hand?
Yes, we hear you.
Okay, very good. So let's start right into the talk, and I would like to just show a little bit about the things I'm doing, because we are going to talk about like a small fraction of things that I'm usually covering, and if people are interested in working, collaborating on different things, they can basically contact me. So there's like 4 pillars, let's say, that I'm working on, and they're all connected, so to say, to performance related things. Like one is performance analysis, usually in the context of MPI and OpenMP, so how to profile or trace efficiently. And we will also see several clock synchronization algorithms and how they what their role is for measuring and benchmarking MPI algorithms. And also, like, I've spent quite a significant fraction of my time on reproducible research, trying to understand how we can make, especially measurements in HPC, more reproducible. At the same time, performance analysis and performance prediction, they somehow go hand in hand. Once you understand what the problems are, you try to make predictions of what you can do better, or if you can model the way you do things, and especially performance modeling, how fast special algorithm is going to be, or how much energy you would like to know how much energy you waste or use for running a specific HPC machine, HPC application on a specific HPC machine. And usually these things require some sort of simulation or analytical model. So for example, using SimGrid in order to simulate the performance of MPI applications or machines, or we might run into auto-tuning problems, and that somehow is related to all these things. I'm also doing quite a bit of algorithmics in the context mostly of MPI, how to, for example, message combining algorithms for collectives, or process to node mapping strategies that I call here. So that's a big problem in HPC. Usually you have a bunch of threads or processes, and you start them up, and the question is, on which core do I put each process in order to improve your performance metric? Usually you would like to minimize the runtime. And then there's also scheduling algorithms that come into play, theoretically and practically. For example, back of task applications. So we have typical parameter sweep applications, and how do we do that in practice or in theory? Also, when we talk about OpenMP, when we have a lot of parallel tasks in a more practical way, how would an OpenMP system schedule these tasks efficiently onto a shared memory system? But in general, I see myself more as a practitioner, but I'm a practitioner with this kind of theoretical understanding of things. I'm trying to understand whether my model, my algorithm that I have in a theory setting that is derived from there is actually working well in practice. And we do that by running experiments. And so as a practitioner, I can basically only observe and measure the runtime or some metrics. And there's 2 things that I'm basically interested in. One is this model versus algorithm. So my algorithm is something that I've implemented already. And I'm interested in, well, whether the expected performance is matching the actual performance on the machine. And if it's not, I ask myself why that is the case and try to find some solutions. And more importantly, I would like to understand once I have implemented two algorithms, like when I see that A is faster than B, if that's like a minimization problem, then I would like to understand, is that a result of chance? Is this just some artifact that I've measured? Or is that somehow generally true? Or in which cases is it true? Because it's usually not always true. Because I'm not satisfied with just having one single run, especially with all these parameters on HPC machine, and then just claiming that A is better than B. But coming, a bit, getting a bit more focus here, I'm talking here about MPI and MPI collectives. So now that you're all in here, I'm just curious, like how many of you have used MPI, like actively or passively in your daily research? So you basically run MPI programs on an HPC machine. Can you just show your hands? Or okay, 1, 2, 3, more. Well, it's at 50%. The others are too shy and not there anymore. Okay, I mean, quite a that's like significant fraction of people. So if we had 100%, I would skip that. But when we have an HPC machine, virtually all applications nowadays run through MPI, at least if you use several nodes. And one way or the other, maybe you just don't see that you use MPI. And MPI is this specification of a communication interface. And we basically have a lot of functions. These operations are defined as functions, and these functions have defined semantics. So for example, we have a send and a receive call in order to send data from A to B, and everything is process-based. So we talk about processes here. We start processes on one machine, and we need to transfer data to another machine. And each of these functions has these defined semantics. And since we only have these functions and specifications, then there are several libraries out there that implement these functions. For example, OpenMPI or MPICH, InterMPI, CreMPI, and so forth. So usually when you get an HPC machine, you have your compilers, and you also have your library that works well with your interconnect, let's say with your InfiniBand network, and so on. And a particular group of these functions is called collective communication operations. And they are specifically done for a group of processes, because we start a group of processes anyways, but usually we can, of course, send data point to point between these processes, but oftentimes you just want to have all the processes doing something at the same time. So for example, we see that core here on the right-hand side. We have typical examples of the most common collectives, or reduce, all-to-all, and broadcast. So in the broadcast is a very popular one. So these are like in a two-dimensional way. We have some data that is owned by one process. So here is process 1 or process 0, however you want to call that one. And this one owns the data. So when we broadcast that package, and once the broadcast is done, the semantics say that all the other processes here in that Y dimension all have the same copy of that data item. So that's my broadcast. And the others, like all reduce and all-to-all, can be defined similarly. And these collective communication operations are important because they are just predefined there. They are optimized because these kind of operations happen regularly. We need to broadcast data very often. We need to all reduce very often, and so on. And that's why they are already there. And but it doesn't stop there. The question is, what we just saw is that we just have these defined semantics. The semantics say, in the beginning, data is at some place, some location, and some process. And after the operation, data has to be copied to all the other processes at a specific buffer. And the question is how to do that. And there are different ways of doing this. And that's what I call an algorithm for implementing this collective operation. And there are, for example, several ones for broadcast, and I show you here too. You can create a binary tree, for example, and this one, the root of the tree has the data item, and it then sends the data to the children. And after a logarithmic number of steps and a number of nodes here, like the last nodes also have the copy of the data. So each node receives the data and then passes passes the data on to the children. Or you could use also a chain algorithm here. So one process owns the data and it creates virtually a number of chains. And then it sends data to each of these chains, and each chain is then responsible for passing the data through that chain. And the chain algorithm is, for example, a nice algorithm for broadcasting large messages, where these messages need to be cut into smaller segments, and then you can use these pipelining effects and use basically benefit from the pipelining in these chains in order to make an efficient algorithm. So we have these different algorithms for these collectives, and we have these parameters for these collectives. So we don't have just this one chain algorithm, but the chain algorithm can look differently. So the question is, how many of these chains do I want to have? And also, what is the segment size? If you want to do this pipelining, if you have a large message, how large are these chunks? So that gives us some kind of flexibility, but also a problem in order to figure out what the best algorithm is going to be. So what is my problem here? The problem is, in this specific scenario, that I would like to find the fastest collective algorithm for a specific use case. And also, I would like to answer, when is this algorithm X faster than Y? Because like, do I have some sort of understanding of when that happens? And if I can do that, can I predict which is the best algorithm for an unseen problem? If I know, for example, I can broadcast data very well with 1 megabyte of data and 32 processes, can I also make a prediction about 64 processes or 1,000? And of course, usually when you do these kind of things, you don't do this only by analytic models. You need some kind of measurements. You measure some things here, measure some things there, and you try to obtain a model. And the question is, how many of these measurements, data points you need in order to make a good prediction? You would like to, of course, to minimize that number of measurements to be cost effective. And even further, the question that we would like to ask, can we do that all online? So we don't want to do measurements beforehand. We would just like to do that while we run the MPI application. And so now we come to some of the work that I've been doing, but I don't work alone. So I would like to acknowledge these 5 researchers that I've collaborated with on these particular topics. So Abhinav Patel, Alexander Karpen-Amari, George Kozilka, Jesper Larsen-Treff, and Sebastian Steiner. And also, because we talked about this previously, I'm glad that I have this PRAISE project that gives me compute hours there at CEA in France. And without that, I wouldn't be able to do all that research. So I'm really grateful for PRAISE for allowing me to work on these machines. And so the problem statement is the following. So we can call that also algorithm selection and algorithm configuration, as in the AI community, which we are not in, but they call it like that. So we have that collective communication problem P, and what is the instance that I'm getting? So I have to solve some problem. It's a collective, the MPI broadcast, for example, a message size, the number of compute nodes, and the number of processes or processes per compute node. Sorry, that should be processes. So how many processes do I start? What do I need to transfer? How much do I need to transfer? And what is the actual collective? Is it broadcast, all-to-all, or reuse, and so on? And the output should be the fastest algorithm that solves that problem P. And for that, we need to solve 2 sub-problems, so to say. One is finding the best algorithm and the best parameters for that algorithm, or a combination of those. So it should be, for example, this broadcast, the chain algorithm, with a segment size of 1 kilobyte, and it should have 4 chains. That's what I would like to have. But for doing all this, like 10 years ago or so, when I tried to start working on this, I stumbled upon some very important thing. So I tried to understand how to measure the performance of a collective, and that wasn't that easy. I thought it would be, but all the benchmarks out there that are still out there today, they give you some kind of performance number, but these performance numbers were not reproducible in the way I wanted to have them. And also, it wasn't really clear what it means by when they tell you something about the latency or the time it takes to conduct a call to MPI or reduce, like what does it mean? And I give you a few flavors of all this. And that's a general problem of measuring anything in the distributed system. So the notion of time is not always the same. Like when you have a distributed system, what an HPC system mostly is, and they usually have different clocks, like each compute node has its own clock, unless you are working on a blue gene. But most of these systems, probably also the one in Cyprus, I don't know yet, but I don't know actually, but I'm pretty much sure that all the compute nodes have their own timers, and they get synchronized every now and then through some like NTP clock synchronization thing or something else, some protocol. But this makes a huge difference when you time things, especially in a microsecond range. But anyway, in order to measure an MPI function, whatever it is, you need to take some timer before and some timer at the end. And each process has to do that. Process 1, process 2, process 3, and so on. All these processes do the same thing. The question is, what kind of timestamps do they get? Well, that's one problem. Like they don't have the same timestamp. And well, you can also measure like how much time is spent here, but also that might not be the same. But what I want to show is there's two ways of synchronizing these operations. So what usually happens is when you do something in a benchmarking setting, you're trying to do many samples of something. You measure all reduce, you measure another all reduce, measure another all reduce, and so on and so forth. And after every all reduce, you just make sure that the all reduce is done. And you do that by putting a barrier in between. So that's a usual, typical way of just making sure that things are synchronized. But the synchronization with the barrier just means that all the processes have seen that barrier. It doesn't mean that they came out in a timely manner. It can be kind of skewed. Whereas in some other benchmarks, you might see the following picture, but might also be interesting for other distributed systems. So you synchronize your clock. You have one global clock, a virtual global clock. And then in the beginning of your measurement, you decide on a start time in the future. Let's say we all start measuring at 4 p.m. So everyone has the same clock, ideally, and they wait for 4 p.m. And when it's exactly 4 p.m., they start measuring the function, and they get the time, and the time in the end, and the time after the function, and after the function and before the function, and we can get the exact timings. And that might improve the situation. And I just want to show you here that the barrier, especially in this microsecond range, might have a huge impact, especially with all reduce. So all reduce is basically used for all the iterations of algorithms that are out there, to check whether something has converged or defined the minimum maximum value after each iteration and something like that. So and what people usually do is like they all reduce 4 bytes or 8 bytes, a float or a double value. It's usually one value. That's a very typical scheme. So when you do that, when you try to find out how long your all reduce takes, you could take different benchmarks. So here are 3 benchmarks. The IBM is the Intel benchmark, the OSU is the OSU Ohio State University benchmark, and the RepRMPI is our benchmark. And depending on the barrier implementation, because we can switch the barrier implementation in the library, like all these libraries, and especially here OpenMPI they have like 10 algorithms for a barrier. And here what we see is we just change the algorithm of the barrier and run that code here. Run this code and just use a different implementation of the barrier. And the outcome, that's what the benchmarks report. For example, Intel reports here, the runtime of all reduce is between, let's say, 75 and 50 microseconds. Here it's between 50 and 100, and here it's between 60 and like 125. And it's just a different way of measuring and a different way of doing the barrier. But what is the runtime now? That's not really easy to tell. I mean, you didn't do obviously something wrong. You just measure like that, and you might be here, or you might be there, and you see that these values themselves are kind of stable. It's not that they vary a lot. So the barrier has a huge impact on what you will actually see. And also, if you measure like that and you try to infer later what is best for application doesn't necessarily have to be the best. So what I just want to say is we have to be careful if you measure something offline and you try to move that knowledge into an actual application, that this doesn't have to be the best case anyways. And the same is with the clock synchronized version. So if you use this version here, we synchronize clocks and we wait for the time, which is this blue bar here. Our way of measuring globalized clocks, these global clocks, or you have the OSU micro benchmarks. This just does this way with some barrier implementation, and we do that here on the Titan at Oak Ridge. I mean, Titan that was the best machine back then, like 4 years ago or 3 years ago. And we see there's a substantial difference in what is reported by all reviews. I mean, it's still the same code. It's just a different way of measuring, whether it's like 35 micros or 50 micros. And that makes a huge difference in order when you try to tune something, that you need to make sure that you actually know what you're measuring. And another problem is reporting factors. I mean, that's also a common problem in all kinds of sciences, let it be chemistry or physics. You need to know what the factors are in order to report your experiments. But also in HPC, in that for this kind of collective setting, we have that problem with the factors. So I just have two factors here. One is the process pinning, and one is the CPU frequency. On the left, what I show here are distributions of running all reduce with 16 by 16 processes. So I'm just running that loop here previously, and I collect that data, the runtime that it takes to complete that call. So sometimes, we see here there's 2 modes, which is interesting, but a lot of these measurements are here in the 70 microsecond range. Sometimes it's a bit longer, sometimes a bit shorter. But so basically, I'm just sampling that all reduce and look at how long does it take, and so on over all these processes. And I get these kind of distributions for 1000 bytes, 4K, 8K, and 10K, let's say. And there are 2 interesting effects. One is the data with the pinning and the no pinning. So pinning means the processes that I start are pinned to a specific core. That is usually almost done by default, by Slurm nowadays, or whatever you do, but usually they are already pinned there. If you don't do pinning, then the processes can somehow float around on the shared memory system. So you have 32, 64, and so on cores on the system, and they might be rescheduled by the operating system as the operating system wants to have it. But just using pinning or no pinning has a significant difference in runtime. And especially for collectives, for these short-lived things in the microsecond range, it gives you a huge benefit. But interestingly, there's also the problem with the CPU frequency. And this is just one stunt here that I saw at some point. So usually you have 2 libraries. And for example, you would like to know whether the all-reduce algorithm in library A is better than B. Or usually, like we ask ourselves, we come up with a new scheme, a new all-reduce algorithm, a new broadcast algorithm, and so on. And you would like to compare our performance against the performance of the others. And that was somehow the interesting question. And in this particular case, we used 2.3 gigahertz of each core that we ran on. So that was the maximum frequency on that particular machine. And so we set it, fixed with DVFS, fixed it, and we compared the all-reduced performance of MPICH and NEC MPI. And these are the distributions of data that we get when we do that, 2 to the 6, 2 to the 7, and so on, bytes that we always all reduce on. So a relatively small number of bytes. And you could say that MPICH here, like it's better here, distribution-wise, better here, better here, better here, and here is kind of indistinguishable. But you would basically claim that MPICH is, is superior. I would use this one. But we have to be careful exactly what we said with the factors. So at some point, we were just trying to be energy efficient, and we rescheduled things, and we noticed that something is really strange, like it's really slow now. And so we did the measurements again. So we put it onto the lowest frequency state, and now we ran it, and it's an all reduced, so it's doing something in a processor, but it's expected to be slower. But it was now huge difference. I mean, NEC MPI was, was always less than 100 micros which was not true for MPICH. So at this point, we couldn't say that MPICH is always the better one. So we just have this tiny fraction. It might work for a pinned version and a CPU frequency of 2.3 gigahertz, but if settings change slightly, the algorithms might take a hit, a huge hit. But now coming back to all this, so we at least had some understanding after a couple of years how to measure correctly, or at least how to measure in a reproducible way, and we knew about the error that we are doing when we measure. Now we try to actually improve the performance of these MPI algorithms effectively. So coming back to the problem again, so we have our machine, we have the library, and we have the library that uses all these collectors. And a specific example that you might have, you have your application running, maybe on 16 compute nodes, and you start 16 processes per node. So in total, you have 256 nodes, you run your physics application, and from every now and then, it does an MPI broadcast with 1 megabyte messages onto all these processes. Might happen. Question is, so which algorithm should I use now on that particular machine? It's really machine dependent and library dependent. You don't really have a universal way of doing this, and not that I know of. It's too complex. So the question is, and also how to set these parameters for the collective algorithm. How many chains, segment size, and so on. So that's how it looks like. So we have our code, a communicator, some array that I would like to broadcast. My root is 0, so I broadcast from that process 0 on. And then there's something in the beginning and something in the end. We don't really care here. What we care about is the broadcast call in our C code. It can also be Fortran, but we want to do that. So 100 ints from root onto all the other processes. So what happens? What is the current, or usually, I mean, the typical methodology? So the user runs with 256 processes, and there's some fixed decision logic in OpenMPI, in MPICH, in MPICH, and so on, that is hard-coded in there, and it does best effort way. So you go in there, and then there's lots of if and else's, some kind of decision tree. And it tells you if the message size, for example, is smaller than some fixed constant small message size, then we use the binomial tree algorithm. And if not, if we want to do something else, then we use the intra-split binary tree. And if something else, then we do this. So we have all these cases, and at some point, the library picks for us a specific algorithm. That's how it works. And here in this particular case, the small message size is 2000, so 2K bytes, and we are just broadcasting here 100 ints. So that is, I have to be careful here. So ints, that's 400 bytes, so it should be 4 byte. We are smaller than small message size. That's the case, and we basically OpenMPI will pick that binomial tree algorithm for us. So far, so good, but might not be the best case. I mean, it just illustrates the problem. So we have something fixed, might not be the best choice for us. So what we like to do instead is, once we get that input, the collective, how many, the message size, so and so many bytes, the number of nodes is basically hidden in the communicator. We know how many nodes we have, and we also know how many processes per node we have. So this is our problem. And then we have some kind of algorithm selection model, and we use some regression models in there, and it tells us, use this algorithm with these parameters. So this is what we would like to have. So what do we do? Well, we do an offline approach here. That's what I showed before. So we have a lot of problem instances that are relevant, that we call relevant. So for example, an OR gather of 16 nodes and so on. So we have a lot of these problems instances, and we benchmark them. We have our benchmark suite, and we benchmark a whole bunch of data points. We sample them in space, and we get the runtime of these particular calls here in our data set. So now we have the data set, and with this data set, we put it into a machine learning program. We have a machine learning task, and we are trying to build a good prediction model with that performance data set, such that then if we have an unseen problem, for example, an OR gather with only 8 nodes, or with a larger number of message sizes and so on, with a bigger message size, that we get a good prediction of the algorithm that we would like to have. So once we have that, we can then query our model, and it gives us the algorithm ID. So that's the general framework, typical offline machine learning problem. The question, of course, is, for which configurations do we actually work on? I mean, or do we benchmark for? And there's certain papers out there that try to do it in a more machine learning way, trying to find the best next point and so on, and trying to sample. I'm more using the, let's say, engineering point of view. I look at the Slurm statistics of the current machine, and I know what number of nodes is the most typically used on the machine. Well, we see that also in the Parallel Wroclaw archive by Feitelson. We see specifically how large the jobs are in the majority number of in the majority basically in this log. So most people use 4 nodes, 8 nodes, 60 nodes. We can actually see that in the Slurm logs easily. And like my approach is, so once I know that most of the users use 4 nodes and 8 nodes, let's just basically benchmark for those and try to build a model then for the ones that are not that often. I mean, I'm using like compute nodes that are not that happen that often. And also the processes per node is a question, like how many processes do we start per node? And there's usually a typical thing, like we have 1 process per node. A typical thing if you just have OpenMP across the entire node, or we have 2. For example, usually we have 2 sockets and we start 1 process per socket and do OpenMP across the socket, or we have as many processes as we have cores on the node. That's a typical thing. And when we have this, we get our data set, or basically our initial data set for the training data set. We know what to do, and we can then start measuring, for example, a broadcast, these message sizes that I have predefined, number of nodes, PPN. And the interesting thing is, so what do I have is this one. So this is going to be our feature vector, the collective message size, number of nodes, and PPN that goes into our model. And what I would like to predict is the runtime for a specific algorithm. And what is our algorithm? The algorithm is exactly that. The algorithm ID internally, oops, why is it moving? So the algorithm ID is the algorithm ID that is internally encoded in a library like OpenMPI and so on. They have their own naming scheme. And we combine the algorithm ID with the segment size or whatever parameters we have. In this case, the segment size for OpenMPI, we combine them to unique large capital algorithm ID. So we might have a lot of algorithms in our Notion algorithm ID, and the algorithm ID in our set encodes specifically a specific algorithm and the parameters. So when we know, for example, our algorithm ID 10, we know that is broadcast with 4 chains and segment size 1K, and so on and so forth. And we might have 50 different algorithm IDs. And what we do is, for each of these algorithm IDs, we build a regression model in order to predict the runtime for a specific instance. And so I already said that how to do that. We do that. And once we get then, we run our program, and it tells us, give me the runtime for broadcast with 16 bytes on so and so many nodes. We go through all these regression models for all these different algorithm IDs, try to make a prediction of this. We get some value, and we try to find the algorithm that minimizes these predictions. And this is the output. And that works much better than many other things that might be much more complicated. And as I said, our algorithm ID output encodes the collective algorithm and the parameter settings. So from this, we can directly translate into the actual solution in the library. So what did I use for the regression learners? What did we use? So we could have, we also did some deep learning, but the data is not that big. So we have roughly, we'll see later, about 100K data sets or less. And the question is not to find the best machine learning. It was not to optimize the entire thing or finding the best way of optimizing. The question was really, can we get away with something very simple that we can implement? And that's not that hard to implement. So we used these 3 methods, the generalized additive methods, because we looked at the relationships between these different points, and it was clearly nonlinear. So that would have been might be a good fit. Or XGBoost as something as a very straightforward algorithm for doing these regressions. And we also use KNN, and it was just to see that if KNN works, well, then there's not much machine learning to be done. It's just as a baseline for all these regression methods. If we just always sample in space, very the closest one, and if we can get away with this, maybe that's also a good way of dealing with that problem. Then we don't need to do any more fancy machine learning. But KNN was by far the worst of these three. So I'm showing results here, basically on this machine called Hydra, which is our own cluster that I played with. We also ran it on the supercomputer NG through Praise. And we used there the Intel OmniPath and the OpenMPI as well. And that also worked, but I don't show results there if you want to know more about the supercomputer NG, because we only use a small number of compute nodes there. So we would like to know, like, how would that translate to 2,000 compute nodes or 3,000? But we only had 32, so it was in the same range as Hydra. Here I just want to show you roughly how many samples we need, because that's important. So in order to build the model for broadcast, for example, on one of these machines called Hydra, we have a lot of data to sample. There's like 250,000 of these samples. So these are data points that we sample. For example, in all reduce that we run 100 times in order to get the mean or median runtime is one sample point on a specific number of nodes. So for example, 32 compute nodes, 32 processes per node, and one message size, and a particular algorithm, and so on and so forth. So we need quite a few samples in order to build some kind of machine learning model. And 250,000 is not much for deep learning. But in order to get the data, that takes quite a while, and that's a problem. So it might take a few hours, maybe a day, to get all this data in. So, but what is the actual outcome? So what I show here, so I train the model on, for example, 16 by 32, 32 by 32, and so on, like the most common scenarios that I find in the logs. And then I'm checking whether my prediction also works well on settings that I haven't trained for. For example, with some obscure numbers, like 27 nodes and one process per node, 27 with 16, and so on and so forth, and also 35, and so on. So 6 different cases that I haven't seen before. And there are 3 bars. One is the best, the exhaustive search best. So I'm trying to find exhaustively the best algorithm for that. I'm not really sure that's always the best, but because there are too many parameters. But basically, we normalize the data to this exhaustive search best, which is usually at 1. And then there's the default decision logic, that's the red bar. And the prediction is our predicted algorithm and the performance of that predicted algorithm. So what I would like to have in the ideal case, that exhaustive search and prediction are the same, and the prediction is always better than the default one, or at least not worse. So when we look at this particular graph, we see that here we are basically matching the default performance, but in most of the case, we are basically matching the performance of the, oops, why is it doing that? Of the exhaustive search algorithm. So very good. So we optimize this case. We also improve. We don't run into this problem. So clearly the library for these kind of message sizes doesn't pick the best one or like a very efficient one. It actually picks an inefficient one, and we try to avoid this, and we do that. Of course, there are some cases every now and then where when we learn, we might also learn something wrong. And so there are a few cases where we actually don't improve, where we slightly make things worse. But overall, the approach works actually very well. This is with the GAMs, and it's somewhat similar to the XJBoost, so they didn't make a big difference. And we have similar results on the supercomputer. Sorry. So, but it was the offline approach. What kind of bothered me on this is always this question, the benchmarking task. Benchmarking takes quite a lot. It might be good, it's a good approach somehow, but I would like to answer the question, like, which cases to benchmark? Like, as I said, we can look in the Slurm job. So I asked the people, like, what are the typical sizes that you use, and you benchmark for those and then infer for others. But it's always kind of hard. I mean, the number of compute nodes is not really the problem, that the message sizes are a problem. So you need to predefine somehow what you measure for. And people typically don't use an all reduce with, 1 gigabyte of data. But if you don't have data for this kind of scenario, if someone is going to do it, you make just a very wrong prediction. So putting it into your data set will improve the performance if someone comes up with this. But usually it takes a long time to benchmark things with message size that are very big and maybe useless for most of the users. So that's also the problem, is that oftentimes it's irrelevant. So the idea is, yeah, just do it online. We execute our HPC applications and we try to use the timings that we get from doing when we run the collectives in the application, when we use something like AMR or some AMG or Chromax, Lava MD, these kind of applications, they are running their milk and they're doing collectives anyways. Just time these collectives and try to find out what algorithm is good there. So the goals were how to build this prediction model with low overhead and higher accuracy from running something on the machine. So our hypothesis is that we can get this efficient prediction model while we run these HPC applications on a production system. And we do that by algorithmic sampling. So every now and then, when an application is calling MPI broadcast, we intercept this broadcast. We change the algorithm that, for example, OpenMPI is trying to do. We just pick our own. One from OpenMPI, of course, or something that is in the library. But we don't let OpenMPI do it. We do it ourselves. And we sample this. And we also do that in a sampling way. We do that every now and then for different algorithms. And we don't do this for all the processes because it will just be too big in terms of space. We just pick a few processes every now and then that do that. And we hope to get away with that. And we do. So the contribution is we have a small first contribution. We call that OpenMPI call tune. And the idea is it's an extension of one of the latest branches of OpenMPI 4.1x. So we encoded all that directly into OpenMPI. And what we're doing is as I said, we intercept the MPI collectives directly in OpenMPI, and we collect performance benchmarks in there. And how is this done? So the question is which algorithm to pick every time. And we don't want to use some kind of uniform distribution. We do that initially. We have a large set of algorithms for broadcasts, for example, with different segment sizes, and they all start out kind of with the same probability of being selected. Some of them are blacklisted before because we know they are not going to be effective. We know that. For example, a linear algorithm on 10,000 cores will not work. So they are blacklisted. We don't even try them. And all the others have an equal probability. So then we run this, and the more data we get over time, the more knowledge we have on how fast these individual algorithms work, and we adjust these probabilities. So small, short-lived algorithms or fast algorithms will get a higher probability, and slow algorithms will get a lower probability of being selected later, but they should not be completely avoided because in the beginning it might be a result, a result of chance. Some other workloads are in the background and they just interfere very badly with some of the timings of one algorithm, and they might actually be effective. So we try to balance that out. And the idea is that we have this very low overhead. And you can see that there. And with the other question is how we model the entire system. So what we use is some kind of a 3D model. We divide our search space, so to say, into 3 dimensions, in exactly the dimensions that we need: the message size, the number of nodes, and the processes per node. So we have these different blocks here. So we cut our search space into all the individual boxes, and each individual box holds a specific probability model, because that's only, like, for example, what we consider is that the runtime in one box is the same for all the message sizes and all the nodes. So for example, let's take this yellow box, for example, what we just because we have to pick ranges and bin things. So our claim is that the runtime of an OR reduce from 64 to 128 bytes between 16 and 20 nodes, and for example, with 4 processes per node, 1 to 4 is always the same, or kind of the same. They should be in the same ballpark. So once we have this, we put the performance numbers into this ball. into this box, and then from there we learn the model. So for example, in this particular box, we have these different algorithms, and it tells us these are the OpenMP algorithms, for example, like a linear one and some binary tree or binomial tree and so on, different segment sizes. Some of them don't support segmentation, and we have these probabilities there. So this one, for example, might be here the best one. It has a 30% chance of being selected. And we do these probabilities for all the different boxes. So we learn all these boxes at the same time. And whenever we get new data, so someone ran a new program, ran GROMIX again with a different message size, we just put them in there. And over time, the model gets more accurate and accurate and accurate, and so on. So the approach then works as follows. So we have all these applications here. These are the different EXA-mini MD and AMG and so on. It's these exascale proxy applications. We run them through Slurm with our OpenMPI specific OpenMPI library, and we intercept these calls every now and then and get these performance numbers, all reduced with this algorithm and so on, has this runtime. So we collect this data. And once we ran our program to the end, we put this performance trace into our model. Exactly as I said, we put them into the right bins and throw them in there. And every now and then, that's the question, of course, like how often do we do some machine learning? We can do this after every run or every day or every week. We update the entire model, we learn something, and then we can make a feedback to this because we have learned and we have now updated probabilities. Or we could also say, like, once we have the problem, what I mean is by probabilities, it just means that like all of them have some kind of a chance of being selected. But you could also say, at some point in time, just now I just want to have pick the best one that you have seen so far. And so we pick the best one that has the higher probability, and we can, for example, create some kind of OpenMPI tuning file, and it just tells me then exactly for message size 128, use this algorithm and so on with these segments and so on. Well, I skip that for now. And so what, that's an interesting experiment to set up here. So what we are doing in this particular case is we're using mini AMR. It's a typical proxy application for all kinds of AMR related things. So we use 32 by 30 process. We fix it on this machine. So we use the same problem instance. And we are trying to run mini AMR and update our model after every run. And we trace all reduce in this mini AMR. So what we want to do is we would like to find the best all reduce just by running mini AMR and update its probabilities after every run of mini AMR. And what we see is here in the beginning, we have these 8 algorithms from 0 to 7. In the beginning, that's the number of iterations of doing these mini AMR runs. They have an equal probability. We just have all of them, the same probability, like 1/8. And what we also see that these algorithms 0 and 7, they fade out quickly. So we have some minimum number of, these are adjustable. We have like, I don't know, 5% or something. That's the minimum number that you can get. So they quickly fade out. And the other algorithms, they actually improve performance every now and then, depending on the numbers. But this algorithm 2 seems to be the best. So the highest selection after 30 iterations is algorithm 2. And that might work well. So when we do this now, when we actually look how fast mini AMR works after these different tuning runs, we do the following experiment. We run 20 different runs of mini AMR, 1 to 20, and we just show a few ones. And we compare to our default OpenMPI selection logic. So these are 20 runs of mini AMR with the default OpenMPI, and it varies a little. So that's what it should mean. Like, it's not always the same. Although we have the same allocation, the performance still varies a little, but here the median will be roughly below 19 seconds. And so we start out, tune 0 is just our selection logic that has equal probability for all the algorithms. And of course, you pay some penalty for doing this, because every now and then we choose an algorithm that's actually like worse than the one here that is in default. So we pay some penalty doing it. But after 10 iterations already, like, we improved significantly here the probability distribution, I mean the distributions here of the runtime, sorry. We also improved the probability distributions, of course. And even after 10, so we have 2 versions of 10. 10 is without the asterisk, just means we pick by probability distribution. and 10 asterisk is picking the best one that is known so far. So this is really the best one that we have seen, and with the one with the highest probability. Then, of course, you don't run into the problem of accidentally running in, using a bad algorithm. So you always use the one that you think is best. And after 20, you see there's no huge improvement overall, but you see that the best algorithm has gained a lot of momentum. So it's kind of the same here. The others fluctuate a little, but the best one has clearly then gained something. And when you do this, then you actually improve the performance by like a second or 10% in this case. So with this, I would like to stop. Sorry, maybe I was a little too late, too long, but we'll see. Anyway, I hope you got the point of what I want to show here and what I want to do.
Thank you very much, Sasha, for your talk. Interesting presentation. If there's any questions for Sasha, please raise your hands. Do you have time, Sasha? You said you might have something.
Sure.
Okay.
I have time, of course.
So, Nicolas, please go ahead.
Hi, thank you for your presentation. It was very nice. I would like to ask something practical. When you have to implement these algorithms, for example, to tune your program, this has to be done on the code, right? It's not like you have to change some variable on the compiler. I mean, you have to develop again the code or the softwares.
Okay, like in OpenMPI, for example, you can, let's say if you don't do anything, it uses this decision logic that I was talking about. And if you want to force, for example, a specific algorithm, you know that you have a specific algorithm, you can even set this via command line parameters. You can say, okay, for the already use algorithm 5, and maybe with that kind of message size and with this kind of segment size, you can predefine that. So OpenMPI, when it starts, it will look into this, are these environment variables defined? If so, then use this algorithm. But since we don't have, let's say, handles from the outside to change the algorithm programmatically from within an MPI program, that's why we had to hack into OpenMPI to do that from within, to basically hijack that implementation, because otherwise from the outside, I can just set it globally. Or what OpenMPI, for example, also allows is to use these kind of files. So you pass this on to OpenMPI, and it tells you, okay, for a communicator size of 1024, means for 1024 processes, and for a specific algorithm ID, internally it's algorithm 7, it's all reduced. So we define 3 different message sizes, this, and that. These are ranges from 0 to 4, from 4 to 128, 128 to something. Use these algorithms. So for example, use algorithm 1, use algorithm 2, and algorithm 5. And OpenMPI will then basically use these files and use these algorithms and basically select exactly what you want to select. If that answers the question.
Yeah, thanks.
Any other questions for Sasha?
But anyway, because I just want to mention that, you can very easily get away, probably, if you have large broadcasts and large audios or whatever your code is doing, and you experiment a little with these parameters from the command line, you can get away with improved performance easily. Let's say 5–10%, or it depends a bit on what you do and how much collective time you actually spend on. If you profile your application and you have 5% of time spent in collectives, you probably won't see anything. But if you have 20 to 25%, and then this might actually improve a lot of your throughput.
Okay, Yanni, you have a question now, I see. Yanni, we can't hear you. But to go ahead. Yannis. Okay, we can't. Oh, no, we can't hear you, Yanni. No. If you can type in your questions, then Sasha can see it and answer. If there's any other question in the meantime for Sasha. Okay, so Yanis is wondering about the online tuning. Let's see what specifically. Sorry. Yeah, what specifically would you like, Yanni, to ask?
He's probably typing his long question.
Yes, he is. Let's see what comes
Oh, yeah.
up. Does this happen during the iterative procedure of each run, or is it collecting means after the completion?
What is this happen? What does this? What is this? This online tuning or?
Yeah.
Okay, I get.
think
So what happens is, so we get these files here. Like why is it always doing this here? Come on. So for a few already users that I'm selecting while we run, we measure the runtime of these different processes. And well, I don't know, we don't use the mean there, collecting means, we use medians, but it doesn't really matter. So we put them into a performance file and put them into our model after each run. We just collect the data, the performance data, we put it into this collective performance model, which happens offline. It's not at the same run. So we don't want to interfere with this. So people just run stuff on Slurm. After each Slurm run, we get some performance file and it gets copied to the database. And then the question is, of course, when to update these models. We use like every hour in our tests, or even like less than that for the mini AMR. We just do it after each run. But after each run with a large system, that wouldn't be feasible. You maybe do it once a day. And then because that takes quite a lot of time to update all these models, because we do some also some regression models in there to predict the performance. And yeah, so basically this is an offline thing. So we online get the data, we build the model offline, and then we put the new data with these collective probabilities back to the online process. So nothing like we don't really do online learning that would, I mean, everything online that would interfere too much with the HPC applications, I guess.
Thank you, Yanni, for your question. If there's any other questions for our speaker, please raise your hands.
I was wondering, wouldn't it be feasible to follow the same logic during the iteration procedure? The same, but I don't really understand. Wouldn't it be feasible to follow the same logic during the iteration procedure? I'm not really sure what exactly you refer to the same logic.
Choosing the best algorithm on the fly.
Well, you mean we can do this already while we run. So we know, okay, this algorithm is bad, and we should get it less probability and basically adjust the probabilities while we run. Is that what you refer to? Okay. Well, theoretically we could. But to be honest, like what I think is that we need more, let's say, statistical evidence. So most of the time with one run, you don't have enough statistical data. Maybe you get like you sample from 30 possible algorithms, maybe 5 or 6 in a significant way. That's why we need a few runs that people do on every now and then, and only when we have like what we have is a few thresholds for that model. Only when we have enough data, we update the model. That's the thing, and we probably don't get that in most of the cases. So I don't want to adjust it while we could try to do that, but yeah, we could. But I'm not doing this right now. But of course, that's possible. I just think that we need more data. That's my strong belief, but I might be wrong.
Okay, well, thank you, Yannis. Who's our speaker? Thank you, Yanni, for the question, even through text. If there's no other questions, if there's any other questions for our speaker, please raise your hands now. I don't see any, in which case I would like to thank our speaker. Thank you very much, Sasha, for agreeing to be our speaker today for our seminar series. Our next seminar is next Tuesday by Professor Luca Piferale with the title AI Meets Complex Flows, Lagrangian and Eulerian Data-Driven Tools for Optimal Navigation, Optimal Order Searching, and Data Simulation. But that's next week. Again, thank you, Sasha, very much.
Thank you very much.
Thank you all for joining, and we'll see you again in our next session. Thanks again.
Thank you.
Bye, everyone.
Bye.